Good morning, everyone. My name is Diana Morales, and my pronouns are she, her, hers. This academic year, I've had the wonderful opportunity to be working with my advisor, Dr. Jennifer Sukis, and we have worked together to investigate the behavior of the Simplex algorithm when applied to transportation and assignment problems. Today, I'll be presenting our work using MATLAB to explore the relationships between problem construction and the behavior of Simplex when applied to these special types of problems. But before we get into that, I'd like to briefly introduce myself. I am from East LA. I'm a third year transfer at Cal Poly Pomona, where I'm studying applied mathematics and electrical engineering. Outside of academics, I am a music enthusiast. One thing I pride myself in sharing is that I've collected music from random message boards on Reddit for a while now. My research interests lie in computational mathematics, signal processing, and most recently, I've become interested in coding theory. I've previously interned at the Hyperion Water Reclamation Plant, SoCalGas. I've volunteered as a peer mentor for other first generation students like myself, and I was a Mickey Leland Energy Fellow this past summer with the Lawrence Livermore National Lab. My latest opportunity has been participating with the McNair Scholars Program at our campus, and looking ahead this summer, I will be continuing my research journey by participating in the MSRI UP RAU program. Now let's move forward. Operations research is an interdisciplinary field that has become a part of the larger umbrella of analytics. An algorithm that's often used in order to solve linear programming problems or LPs is the simplex algorithm, which provides optimal solutions for LPs, which we can use to model programs in military, agriculture, and transportation, among other applications. Although it is a finite algorithm, its efficiency has been questioned quite a few times. Previously, researchers have actually shown that there exists a carefully constructed LP that points simplex towards a longer path that results in behavior that is exponential in relation to the size of the problem, where a path is defined as the number of iterations needed to arrive at an optimal solution. Now, before I move forward, I'd like to briefly explain how simplex works in general. So in this figure, we see the construction of an LP made up of an objective function and inequality constraints. The boundaries that make up the feasible region of our constraints, and the corner points are our points of consideration, are, as we call them, corner point feasible solutions. Simplex would start at the origin and move in the direction of most rapid improvement by evaluating the objective function at the point and continue doing so until it arrives at an optimal solution. Now, in this LP, we see numbers such as 2 and 18 in the inequality constraints. However, transportation and assignment problems, which we will call TP and APs, have equality constraints with only binary decision variables. And in the case of assignment problems, we have ones on the right hand sides of our equality constraints. So here we have SI and DI, and so these constraints make sure that only one assignee, or each assignee is assigned to only one task, and one task is only being performed by one assignee. And here's what I'm talking about when I say that our equality constraints for assignment problems have ones in our right-hand side, and as we can see, that will ensure that our variables are greater than one, greater than zero, but less than one. So this structure prevents, as I said, variables larger than one. This unique structure is interesting as it makes us wonder upon the relationship upon problem construction can have on the behavior of simplex. Specifically, we can focus on the relationship that coefficients in the objective function can have in the behavior of simplex. Now, in 1973, as I mentioned briefly earlier, there was two mathematicians, Clay and Minty, that provided us with the construction of a worst-case scenario with exponential time complexity for problems with m constraints and 2m variables. Now, in our construction, we will have m constraints and n being equal to m squared over 4 variables. In 1980, Norman Zadeh, a different mathematician, suggested a rule that could maybe make sure that we had a variable enter the basis that hadn't been entered in a while, so our least entered variable, so that maybe we could kill the exponential behavior found in the worst case scenario LP. And then in 1981, we had two different mathematicians, Observe that when the coefficients of our objective function are sufficiently spread out, such as 1, 100, 1,000, 1,000,000, etc., the path can depend on problem dimension. So after reading our literature, my advisor and I turned to MATLAB to run a number of trials to explore our research question. Do our assignment problems and transportation problems follow a simplex path that is linear behavior or nonlinear behavior? And so the way we did that was we created a function in MATLAB that would take as an input a constant x, which we define as our dimension, and that function I'm talking about would be this lower right-hand corner. And so that dimension x would be turned into x squared variables and 2 times x constraints. Our MATLAB script would then construct the assignment problem, solve it using our built-in function limprog from our optimization toolbox in MATLAB, and return useful information to us, such as the final optimal value that would allow us to see the impact of rearranging coefficients in our objective function, our final basis, which would be the variables that are used to obtain an optimal value, our reason for stopping, which allows us to see if Simplex successfully completed its procedure, and the number of iterations, which would be the path that Simplex takes. This information would then be compiled in a CSV file and then imported into R. So we would have our larger script running or calling our function returning our useful information to the script, and our script would finally, once it was done running our for loops at the beginning, it would then give us a CSV file, which we could then go ahead and use in R. So now diving into our data, we were able to test linear behavior, and we did that doing so like by generating 1,000 problems, and we were able to solve 10 problems of each dimension, and we were able to show that we get linear behaviors when we plotted number of iterations against our dimension. More specifically, we plotted this trend line, as we could see the red line, that we get a slope of approximately 2. Additionally, this shows that there is a linear relationship between our number of iterations and number of constraints, which we recall was equal to 2 times x, and that would have a slope of 1. In the next few weeks, we will be considering objective function coefficients, whose ratios are quite large, in order to understand how the order of magnitude impacts the solving time of Simplex. This would be numbers like 1, 100, 1,000, 1,000,000, etc. And in other words, we'll be using coefficients that are sufficiently spread out. We will then also solve the permutations of the objective function to further investigate how problem construction of our assignment problems and TPs may affect the number of iterations to optimality by Simplex. And so that is what I'm describing here, the permutations. These would be the different rearrangements for our objective function coefficients. In conclusion, we have thus far observed linear behavior in the case of TPs and APs, and we will now be considering sufficiently spread out coefficients in our objective function. So that is what we are looking forward to in the next few weeks. Thank you so much. I'd like to thank my advisor, Dr. Jennifer Sipkis, for her guidance and mentorship in our research together, and for always encouraging my questions as we are coming to see these observations. I would additionally like to thank the RSCA coordinators and the McNair Scholars Program for allowing me to have this experience. Thank you so much for your time, and I hope you enjoyed this presentation. Please feel free to ask any questions at this time.